Good morning. We are in the fourth unit of distributions of random variables, and in this video I'm going to talk about the normal distribution. Okay, the normal distribution, it's also called Gaussian because it was developed by a mathematician called Gauss. It describes probably many continuous variables that we found in practice. Actually, if we measure like length, weight, it makes a lot of sense that if I make a histogram of the values, you have a shape of the histogram like this, okay, a symmetric distribution. It's a typical histogram. This is the typical histogram of a normal distribution. Remember that the density function describes the shape of the histogram, and then this would be the typical density function of many variables that we measure in practice. If I ask a person about the weight or the height, it makes a lot of sense that this is the distribution. This normal model was developed by Johann Carl Friedrich Gauss in the 18th century. It ranges from -infinite to infinite, so there is no minimum or maximum value. This is the way how we express that x follows a normal distribution. This distribution has two parameters, so in this subject we will consider that the first parameter is the average and the second parameter is the standard deviation. If you look at different books, in some books they may consider that the first parameter is the average and the second is the variance. So please pay attention. In this subject, okay, when, for example, if I say n of parameters 10 and 2, 10 will be the average, 2 will be the standard deviation. Well, so the average will be m, the standard deviation will be sigma. It's called a Gaussian bell-shaped distribution. Okay, actually, because this shape resembles somehow the shape of a bell. And something important, remember that for any kind of continuous distribution, the probability to be higher or equal to value is equivalent to, say, the probability to be just higher than the value, because the probability to be exactly equal to that value is always 0. Why? Because if we think about a continuous variable, we're thinking that it has like a lot of decimals. So if you think about a column of values so that all of them are measured with a lot of decimals, the probability to find exactly one particular value tends to 0. Okay, so this is important. So for any kind of continuous distribution, it doesn't matter to be uniform, exponential, or normal. So we will forget about the equal. So we will put higher than, higher or equal is the same. Well, then this is the density function for the normal distribution. It's a complicated formula that I'm going to explain in the next slide. So about this density function. What is the basic structure? The basic structure is this. So let's start with the most simple form. Density function, the exponential of minus x squared. What is this shape? Well, if we make the derivative, this is this shape, this is the derivative. So the derivative when x is 0, here when x is 0, the function is 1. And the derivative when x is 0 is 0. So the tangent line of the region is horizontal. So this is the shape. When x is 0, I reach the value 1. And then when x is 0, the tangent line is horizontal. So it's easy to demonstrate that it is symmetric. Okay, so you can see how actually this is the basic shape of the normal model. Okay. So the average is 0, but obviously I need a function so that the average is m. So we can put the exponential of minus x minus m squared. So this is like the first step. So, but the density function should have different kind of dispersion. So I have to consider one parameter so that dispersion can be different. So let's say that I multiply the exponent by a coefficient b, so that the width or the probability of this density function can be different. And then important, remember that I have to multiply by a constant because the area below any kind of density function has to be 1, so that this constant has to be properly calculated so that the area is 1. So now the integration of this has to be 1, then and then the variance by applying mathematical expectation. Okay, this is the general formula. So we have like two unknown parameters, a and b, and then we have two conditions. The condition that this integration has to be 1, and the condition that this integration has to be equal to the parameter sigma squared. So by solving both equations, we arrive at the conclusion that this coefficient has to be this, and this coefficient that multiplies the exponent has to be this one. So finally, we end up with this formula that seems complex, but in this slide, I tried to explain a bit about it. Okay, properties of any kind of distribution. So if x and y are two components of a two-dimensional random variable, so we have that the variance of a coefficient that multiplies x plus or minus another coefficient that multiplies b is equal to this coefficient squared multiplied by the variance of x plus the coefficient b squared multiplied by the variance of the y plus or minus. Okay, so if here I have a plus, here I will have a plus, but if here I have a minus, here I will have a minus. 2 times multiplied by a multiplied by b multiplied by the covariance. The covariance is a measure of the type of relationship between them, so that if they're independent, if there's no correlation between them, then the covariance is 0. Okay, so properties of the normal distribution. So if I have x that follows a normal distribution, if I have a linear a constant plus another constant that multiplies x, so I will have this expression. M is affected with this formula, and the variance is equal to b squared multiplied by the variance of the x. And then if I have x and y so that both are normal with a different average and a different standard deviation, and if they're independent, okay, so starting from this general formula, we have this. So always the sum of normal distribution is always normal. Okay, so there's no requirement. Always that I sum, or if I subtract normal distribution, it's always normal. So if I sum, I will have the sum of their averages. If I subtract, I will have the difference of their averages. But in both cases, the variance is the sum of the variances. Here, we never subtract. Remember, important, the sum of the variances. Okay, for example, imagine that I want to compute the probability that x is less than y. This is not an easy example, okay? Imagine that I have a distribution with an average of 10 and the standard deviation 2. Let's imagine that here the red model has an average of 15 and the standard deviation of 3, okay? So most of the values of the red curve will be higher than most of the values of the blue one. But we want to be interested in calculating exactly that percentage. Okay, so how can we do that? Well, the trick is to put the y at the other side of the inequality. We say that the probability of x being less than y is equal to the probability that x minus y is less than 0. Okay, mathematically this is correct. And then here, what I have is the difference of two normal models. Okay, the difference of two normal distributions. Then we have that this is the probability of a normal distribution with the difference of their means and the standard deviation, which is computed with this formula. Okay. Then this is a normal distribution, and then one important property is that the average plus minus 1 times the standard deviation, it comprises 68.3% of the values, which is approximately 2/3. It's a property of the normal distribution. Okay, then we can say that m minus the standard deviation corresponds to the percentile 16 approximately, and the average plus the standard deviation corresponds approximately to the percentile 84. Then what happens if I consider the interval of the average plus minus 2 times the standard deviation? It comprises 95% of the values, and this is a very important rule in statistics that we use very, very often. The average plus minus 2 times the standard deviation in a normal distribution comprises approximately 95% of the values. This is probably one of the most important rules in this subject of statistics. Okay? Usually, we consider this as most values. So if we have a distribution, if we think, what is the range of most values? So quite often, we consider 95% of the values. Outside, we will have approximately 5%. So m minus 2 sigma will be the percentile 2.3, and m plus 2 sigma is the percentile 97.7. What happens if we comprise the interval of m plus minus 3 times the standard deviation? Well, it comprises 99.7%, which means that 3 values out of 1000 will be outside. So in this case will be like nearly all values. Okay, so in statistics, if we want basically most of them, quite often we use m plus minus 2 times the standard deviation. But if we want to a wider interval that comprises nearly all the values of the distribution, quite often we consider m plus minus 3 times the standard deviation. Okay, so a graphical verification is this. So I obtained this curve with StatGraphics. So like an example of a normal distribution with an average of 10 and the standard deviation of 1. Okay, so if we apply this rule, the average 10 plus minus 2 times 1 is between 8 and 12. So between 8 and 12, we will have 95% of the values, and this is why here outside we have like a small area. But if we apply plus minus 3 times the standard deviation, the range is from 7 to 13, and then we can see that below 7 the shape is nearly flat, and above 13 the shape is nearly flat again, which means that the percentage of values is very, very small. Remember, this is just 3 out of 1000. Nearly flat implies very few values. Well, so one application of this rule of 3 sigma is in statistical process control, when we have independent measures, okay, when we have values that are independent from the previous ones. Okay, so imagine that we have like a sequence of random values that are independent, so everyone is not affected by the previous values. So quite often we use the rule of the average plus minus 3 times sigma. This is a quite of control chart that is called Shehort control chart. It was developed by this expert Shehort in the year 1930s, and we put like some kind of control limits. So when one value is outside the limit, as the probability of happening is so small, this is like an indication that something wrong is probably happening. So that we say that the process has to be revised. The process is out of control from a statistical point of view. Okay, well, so this is the density function, and then this is a value, and then how to calculate the probability that a normal is higher than a value? Well, this is the area, so we should make the integration. So the integration from a to infinite of the density function. So we should obtain the primitive of this function, but interestingly, this integration cannot be solved analytically. So we need numeric methods to solve that. And what is this numeric methods? I'm going to explain like with a simple example. Imagine that I have a integration from 1 to 2 that 3x, okay, a very simple polynomial expression. This is x squared divided by 2. We apply the rule of Barrow, x squared, x equal to 2 minus x squared equal to 1, and then we end up with a solution which is 4.5. Then this is the straight line, 3x, and the area is what we obtain from 1 to 2, 4.5. Now, what is numeric method for the integration? Numeric method is that from 1 to 2, we divide it like in 100 intervals, for example. Okay, let's assume that I have like 100 intervals, and then I have to compute the area of these 100 rectangles. The base is the same for all of them, and then the height, so I have to substitute in the equation. So that would be 3 multiplied by 1 plus 3, okay, so it's 3x, so 3 multiplied by 1 plus 3 multiplied by 1.01 plus 3 multiplied by 1.02 and so on. Okay, so this would be like the height of every rectangle. Remember that the base is the same. So if we make this, I obtained a result of 4.49, which is more or less equivalent to the real solution. So this is like a simple example of what is numeric methods. So if we apply this for this integration, okay, it's easily to program. So we can program an algorithm to compute the numeric integration of this density function for the normal, and then we can obtain the values. Good. So now I'm going to think about one property of the normal. So imagine that I have a normal distribution with an average of 10 and the standard deviation of 2. And then imagine that I have another variable which is x minus 10 divided by 2, or which is equivalent to 0.5 multiplied by x minus 5. What is the distribution? What is the average? And what is the variance? Okay, so in general, what happens if I make this kind of transformation? Well, so the expectation of this, okay, by applying properties of mathematical expectations that I explained in a previous video, we end up with a solution that the average is 0. It's always 0. What is the variance? Okay, well, the variance of this is the variance of x minus the variance of x also, okay, because this is a constant that goes squared, so it's 1. And this is interesting because always that we make this kind of transformation, we have a normal distribution with an average of 0 and with a standard deviation of 1. This kind of transformation is called Z in statistics. So Z corresponds to a normal distribution with an average 0 with a standard deviation 1. It's called the standard normal distribution. It's very important in statistics. Okay, so the probability of any random variable, any normal variable to be higher than a value is equal. So we make this operation. We subtract both sides of the inequality. We subtract the mean. Then we divide both sides of the inequality by the standard deviation. And then here, this term becomes the standard normal. This becomes the standard normal. So we can make this operation, and then we can solve this. Okay, so we can solve the normal distribution by applying numeric methods, but by applying this property, always we end up with the standard normal distribution. So we just have to integrate the standard normal distribution with numeric methods. Okay, so this is why we have the table for the standard normal that I'm going to explain in the next slide. So for example, what is the probability that a normal distribution with an average of 10 and a standard deviation of 2 is bigger than 13? It's equal to the probability that the standard normal is higher than 13 minus 10 divided by 2. Okay, so bigger than 1.5. So by looking at the table of the standard normal distribution, we can find this calculation. Good. So the variable of n01 is often called z. Then what is a critical value? Important, because we will use this concept in the inference, which will be explained in a further unit. Critical value z sub alpha, so is the value so that the probability that the standard normal is bigger than this critical value is equal to alpha. Okay, well, graphically I think it's easier. So if this is the standard normal, so if alpha is 5%, I have to find the value so that above this value I have 5%. Okay, so this is called critical value, and it is represented like that. Z, because it's the standard normal, 0.05, because it's the area, so that above, this is the area that I put above. Okay, so, and this critical value is 1.64. Okay, so I have similar notation for other distributions. This is something that I will explain in the unit of inference. But for example, if I put T9 0.025, what does it mean? The probability of this distribution to be higher than this critical value is 0.025. Or for example, F26, these are degrees of freedom, but above I put as separate index 0.05. It is a critical value, so that the probability of this distribution to be higher than this critical value is equal to 0.05. Okay, so this is just to show you that the concept of critical value applies to any kind of inference distributions, the normal, the student t-distribution, the chi-square of Fisher's F. Okay, then another notation aspect is the following. The probability that normal is less than a value is equal to the probability that the standard normal is less than a minus the average divided by the standard deviation. Okay, this is what I have just explained. So this is like a long formula. Okay, so a way to make it shorter is to say phi. Okay, so actually this is the distribution function. So phi is the distribution function for the standard normal. So putting this and putting this is exactly equivalent. This is used in a lot of books, but I think that it can be somewhat confusing. So I prefer using this notation to avoid confusion, that in my opinion becomes somewhat more clear. Okay, distribution function of the standard normal. Important because it's very often used in a lot of books. Okay, for example, phi of 2 is the same as the probability that the standard normal is less than 2. Okay, for example, a question, z 0.025, is it percentile 25? Well, the answer is no. Okay, so please pay attention. Z 0.25 is the same as percentile 75. Okay, so this is the critical value, so that above I will have 25% of the values, and by definition it is the same as percentile 25 or the third quartile. So please pay attention that sometimes it can be confusing. Okay, well, and here I finish this first part about the normal distribution. In the next video I will explain about the use of the standard normal table. Thank you very much for your attention.